Welcome back, welcome back, welcome back. I'm Lisa Blackburn, and this is my YouTube channel where I talk about everything I want to, science and math. And what we're doing today is elements of chemistry. So this is for the students who are absent today. And we're continuing the notes, hopefully finishing the notes, with the story of radioactivity. So go find that in your notes, and we're going to talk about it. All right, so everybody's got your notes out? All right, so we talked about the atom, and where we ended was the story of radioactivity. Now, there was a guy, Henry Becquerel, I'm sure I'm saying that in perfect Italian, and he accidentally discovered X-rays. Oh, no, not that. He accidentally discovered radiation. Let me make sure I got this on. Draw, pen. Now we want a different color. We'll make it red. He accidentally discovered radioactivity. Okay, so this is what he was doing. He had some glow-in-the-dark rocks. That's cool, right? And what he was doing is he wanted to see if his rock was strong enough to expose a photographic film, to make a picture. Good experiment. And it was the end of the day. It was Friday, time to head off for the weekend. And he took his glow-in-the-dark rocks and his unexposed, still wrapped up in their dark, safe container photographic film, and he threw them in a drawer in the lab and left for the weekend. When he came back on Monday, he wanted to continue his experiment, got out his rocks, got out his film, went to do it, and the film was already exposed. It was like it had the sun shone on it. It was ruined. But there was no sun in that drawer. There was just glow-in-the-dark rocks. And do glow-in-the-dark rocks continue to glow after you put them in a dark drawer?
Yeah.
No, you have to charge them up. Haven't y'all ever got glow-in-the-dark? So you have to hold it up to the light and charge it up, and then you turn off the light and it's green, right? That's how glow-in-the-dark works. We need some glow-in-the-dark to play with, right? So he had glow-in-the-dark rocks, but it exposed the photographic plates, the photographic film, and it turns out there was uranium mixed in with the stuff that was making it glow in the dark. So what he discovered was X-rays, that you could take pictures with these rocks that had the uranium in them, and they had the best time. They took pictures of hands with jewelry on it. They took pictures of skeletons dancing around. They thought it was great because they didn't know it was dangerous and it could give you cancer. They weren't getting, when you go to the dentist and they take pictures of your teeth, how they put that big heavy thing on you to protect you from the X-rays? Nah, they were just having a great old time with them. Didn't know about it. When my mom was a kid even, they didn't realize how harmful these things were. And she said when you would go to a fancy shoe store, not the cheapo ones, but if you went to downtown Atlanta, to the fancy shoe store, they would X-ray your feet to make sure that you were getting exactly the right size shoes. All those shoe salesmen died of cancer because there was no lead blanket. They just had these boxes going all the time with the X-rays in them. So here's our X-ray seeing the broken bone. Well, he had a friend, Marie Curie. She's the most famous woman scientist. And he told her about his experiments, and she continued with them. And what she did she is the first person who started understanding radioactivity. Henry Becquerel got it, he discovered it, but she started understanding it. So she worked with her husband, Pierre, in France in a lab, and where you went to tell people about scientific discoveries was this one place in France where all the scientists would meet. And women weren't allowed to speak there, but that was okay. Pierre was going to go tell them about his great discoveries about radiation and all that they were learning about radioactive elements. But on the way, he was walking there, and he was struck and killed by a taxi cab. It was back a long time ago, and this taxi cab was actually horse-drawn. So he was trampled to death by a horse. So then they had a dilemma. Women weren't allowed to speak, and she's the only person in the whole world that understands the science. So they changed the rules. And she was the first woman to ever be allowed to speak to the scientists and explain them to her. Really, she understood it better than her husband. Her husband was real good at thinking of the experiment and making the equipment, and she was real good at analyzing the data, because we all have our strengths. So she was the first woman allowed to speak to the scientific community. She discovered the elements radium and polonium, which doesn't sound like much of a big deal because, y'all all did those element reports, and lots of people have discovered elements, but it was that she understood something that the men of the scientific community didn't, and she broke that glass ceiling. She got to go speak to them and explain it, and she was really the first person to start understanding radioactivity. Now, there's another person in our story who's also a woman, Lisa Meitner. Now, by this time, time's gone along, and it's the time before World War II. And she's working in Germany with her lab partners, Otto Hahn and Fritz Strassmann, and they are working, trying to understand what would happen if you take these big radioactive rocks and you shoot them with a ray gun. Remember, they have the ray gun, and what do you do when you have a gun? You shoot stuff with it, right? You mess around and shoot stuff. So, but the problem is that Lisa Meitner was Jewish. I do believe, from what I've read, that her faith was Christian, but her heritage was Jewish. Hitler didn't care. He didn't care who you believed in. He cared about your ethnicity more. So her lab partners, I want to stress to you that these were good guys. They took their personal money, put it together, and got her out of the country to save her life. Got her to Switzerland. So she's in Switzerland, and what they were doing is they continued the work because they were Aryan. Hitler wasn't trying to kill them, and they continued the science. And we're doing these experiments, shooting these rocks with the ray gun, shooting these elements with the ray gun, and they got some lab results they didn't understand. So they mailed it to her in Switzerland. She was celebrating Christmas with her nephew, who had also come, and they look at it, and she understood what had happened. They had split the atom on accident, but did it. So she figured it out. It's nuclear fission. So over here, you have a little fish drawn on your lab, right, on your notes. And I want everybody to pretend that their hand is a knife, and I want you to take the fish and chop the fish in half. Everybody chop your fish. Because what kids do wrong is they get these two words mixed up because they sound alike and start with the letter F. But if you will remember that fission is chopping the atom in half. It's splitting the atom. Now, this was a big deal because what war were we in? World War II. And we're trying to defeat Hitler and the fascists. And Einstein has figured out E equals mc squared. So there is a relationship between energy and mass. And when you split the atom, they were shooting it with alpha particles, it gives off energy. And they started figuring out they can make a bomb out of this. So nuclear fission is what causes the bombs. They use that. Now the opposite, what everybody gets confused is if you can take little bitty elements like hydrogen and you can squish them together in nuclear fusion. So everybody pretend like you're making a ball, you're squishing elements together. This is fusion, you're fusing them. This is what is happening right now in the sun. Hydrogen is being squished together into helium, and because of E equals mc squared, the sun is shining. So when your little kid asks you, Mommy, Daddy, why is the sun shining? You could say, well, it's nuclear fusion because of E equals mc squared. Now you know. Okay, everybody knows where this comes from now. It makes sense. So the next guy who came along was Enrique Fermi, and this was actually part of making the bomb too. He was the first person to control a chain reaction. So to get the bomb, you have to have enough stuff to make it, called critical mass, and then it has to have a chain reaction. When they first tested the nuclear bombs in World War II, they didn't know if the chain reaction could be stopped. They didn't know for sure if they were going to blow up the world. There were scientists in the group who thought they were going to catch the oxygen on the planet on fire and burn the planet up, and they tested it anyway. That's pretty shocking, isn't it? That's how scared of Hitler they were. They tested it anyway. They decided it was worth blowing the whole world up rather than letting Hitler get it. That's something, isn't it? So that's Enrique Fermi. They didn't blow the world up. They made the bomb instead. Okay, so the atom is made out of, we already talked about, protons, neutrons, and electrons. And there's our chain reaction, dominoes falling over. There's more things called quarks that you will, subatomic particles, mesons, gluons, all kinds of things. Antineutrinos, that one's always fun to say. You will learn about those in physics next year when you take physics. Okay, so, that's the next class after this one. We'll talk more about that this week, what you can take next. Okay, so now we're going to go back to Bohr. Niels Bohr, our guy with the Bohr model, he came up with some models. And we're going to make some models like how he did. His model, remember he was 1913? He wasn't our current view, but he's a good place to start. His models only work really for the first 20 or so elements, but we're going to learn how to do this. It's going to be on your test, which is Thursday, and it's going to be your homework sheet that you're going to do tonight, which is right here. So make sure you pick that up off my desk before you leave so you can do your homework, because it will be part of your packet. All right, so this is how you do it. You start by drawing the nucleus. Then you look on the periodic table for the whole number, and you see, you look at me, Elma, you look and you see the whole number for the element, and this element's whole number is 1. Let's see if I can show YouTube. See the whole number right there, the green one is 1. So that means in the nucleus that there is 1 proton. So write 1p in the center. 1p for 1 proton. Then you look and you see what the mass is. The mass is the decimal number. You have a periodic table at the end of these notes, and I've also given you 2 periodic tables. Get one where you can look at it so you can do these. Make sure you've got a periodic table. Look at it and somebody tell me what the decimal number is for hydrogen. What is it? It's 1. It's 1 that just rounds off, isn't it? If you round that 1.00 something, it's 1. So I'm going to make a Bohr model here. There's my 1 proton. No neutrons, because how you get the neutrons, just like how you did on your homework, is you take the mass minus the protons. 1 minus 1 is 0. 0 neutrons. Does that make sense? Okay, now, if it's a neutral atom, how many electrons would it have? It'd be the same as the protons, because if it's neutral, you have to have the same, which means it has 1 electron in its first energy shell. So you're going to draw a circle for the energy shell and draw the electron in it. So that is the Bohr model for hydrogen. It has 1 proton, 0 neutrons, and 1 electron. How do we feel about that? Now, remember how we learned about the energy shells? The energy shells, the first one can hold 2 electrons, the second one can hold 8, and the third one can hold 8. So write that on your paper, 288, and let's try helium. Try helium by yourself. See if you kind of understand this. Give helium a try. Give helium a try. I sort of want to show this, and sorry, YouTube, you're not going to get to see the other thing on the board because I don't want to mess the photo up. Okay. Okay, so how many protons does helium have? 2. Do you see the big 2 on the periodic table? The whole number 2 means it's got 2 2 protons. What is the helium's mass? What's the mass? What's the decimal number? 4. And what's 4 minus 2? 2. So there are 2 neutrons. Now the protons and electrons are the same, so how many electrons are there? 2. So this is what it looks like. 2 protons, 2 neutrons, 2 electrons. 2 protons, 2 neutrons, 2 electrons. Do you understand this one also? Sometimes they're drawn like this with the balls, and sometimes they're drawn like that with the letters. Okay? Try lithium. Everybody try lithium. Okay, let's see if we can do it. Look at lithium. It's right here. It's got 3 protons. Did you get that right? And what's the mass of lithium if you rounded it off? 7. It's 6.9. That's 7. So what's 7 minus 3? 4. So we have 4 neutrons. 4 neutrons. And how many electrons? 3. 2 go in the first energy level and 1 in the second energy level. Is this easy? Yeah. This is going to be a better test than last one? I think so. Okay, let's try another one. Let's try beryllium. Beryllium is number 4 right there. So everybody try it. Did you get it? Sean? Did you get it? Donald? Did you get it? I have to see eyeballs, not on the top of your head, so I can see understanding there. So don't put your head down. I want to see your eyeballs. That's why I really didn't like it when I had to go to all digital teaching last spring. I couldn't see people. I had to do it all on YouTube. I kept asking the YouTube camera, do you understand? And I think, I don't know. I don't know if they understand or not. They're watching me on YouTube. Got to see those eyeballs. All right, did you get it? So how many protons? 4. How many neutrons? 5. And then how many electrons? 4. 2 and 2. Okay, I'm going to let you finish those and you on your own because I think you got it. And we're going to finish up these notes, okay? Now, imagine that this is an element, okay? The protons can't change. The only way to change those is with nuclear bombs, so we're not going to do that. How something changes its charge is by gaining and losing electrons. Imagine I have electrons here. What charge are electrons? Negative. And imagine if I rubbed off some of this negative off of this atom. What would happen to the charge? It wouldn't be balanced anymore. Would it be positive or negative if I rub off some negative? Positive. And if I put some extra negative on, then it would be negative. So the gaining and losing electrons are how atoms get to be charged. When they're charged, they get a special name called ions. It's an ion if it is a charged atom. So write that out. It's charged. Now, if it loses the electrons, it becomes positive or negative? Loses the electrons, it becomes positive. And if it gains electrons, it becomes negative. Now, there's a special name for these ions. And I'm going to show you how to remember it. kitty cats are sweet, wonderful, darling, positive little creatures, and we love kitty cats. So, a nice positive ion is called a cat ion. A cat ion. And we're going to remember that because kitty cats are so wonderful and positive. See how he's got a positive on his mouth right there? Cats are wonderful and positive. Now, I know some of you might be objecting in your heart, but keep it to yourself because cats are positive. And the opposite of cats is something we can all agree on that we hate. What is that? Can you tell my drawing? It's an ant. So negative ones are called anions. And we're going to pretend that that's a fire ant. And we live in Georgia and we hate fire ants because you go out in the yard, they get all over your foot and they bite you and they leave weird little sores on you that look like pimples. We hate fire ants, don't we? We can all agree on that. So antions are negative. In fact, have y'all ever noticed that there are fire ants trying to build a mound in our classroom right over there by the door? We got to get some Raid. Put some radon on them. Because there are fire ants right behind my desk in our classroom. Terrible. We hate them. Much rather have a cat over there than some fire ants behind my desk, wouldn't you? Pretty much. All right. So we're going to learn a little bit. You learned a little bit about that in your Inside the Atoms 1 and 2 homework you were supposed to do. If you didn't do that homework, you need to do it. I'm going to post the answers as an announcement on Canvas. I want you to check your answers, and if they're wrong and you don't understand why they're wrong, I want you to ask me in class and we'll go over it. Does that make sense? So I want you to check your answers. I don't want to do it yet because I want you to have time, everybody have time to do it. Now, atoms can be charged or they can be neutral, but they can have more or less neutrons. The protons are what makes an atom what it is. The neutrons, you can have more or less. The atom could be fat or thin. It could have more or less neutrons, and it's still that atom. You might have heard of carbon-14 or carbon-12. Those are different isotopes. These are fat or thin atoms that have more or less neutrons, and some of the isotopes, especially fat ones, can be radioactive. So that's why, isn't it on The Simpsons that the baseball team is the isotopes? Isn't that right? That Homer was the character for the isotopes? I think so. Y'all can correct me if I'm wrong. All right, so these big fat isotopes that are radioactive can fall apart. They can start shedding a radiation, atomic particles, like alpha, beta, and gamma. Now remember how we talked about the ray gun that was shooting alpha particles? That's this. The symbol for it looks like a little fish. The symbol for beta is like a capital B that doesn't quite close. And the symbol for gamma looks like the Aries ram's horns in the zodiac stuff. Now, there are more symbols for it. Alpha particles are actually helium atoms, so sometimes it's written like that, with the mass of 4 and the number of protons is 2. So 4 is the mass, and 2 is the atomic number. Beta is actually an electron. And it is sometimes given this symbol because it has no mass and it has no protons. It's almost an antiproton. So it's a -1 and a lowercase e. Remember I told you lowercase e is the symbol for electron? And that's how you can remember electrons are negative because it looks like a negative inside of a circle almost. Gamma is light. Remember Ronald McDonald is very ugly, extra gross, is all types of light. So this is, what turns Bruce Banner into the Hulk. So I've never gotten to have superpowers yet, even though I'm in a lab. But so it has no mass and no protons. So its little thing is 0, 0. So that's kind of fun. These are Greek letters. Isn't that fun? Don't you feel smart learning a little Greek? It's Greek to me, right? So that's what those are. Now then, I think we got all of that. Got all of that. Okay. Now, so another thing is you can write here, examples of isotopes are like carbon-12 is what you mainly are made out of. There is a radioactive form of carbon called carbon-14. These numbers are the mass. That's the mass, or those numbers that when you hear that. Okay, the last thing that's on this test is the periodic table. You have to know the areas of it. So we're going to color it and talk about it. Now, the first we have two general areas, metals and nonmetals. So get a color. I'm going to use red. And we're going to draw the metalloid stair step. Excuse me. Not the COVID, it's spring allergies. I get them all the time this time. And I don't like taking the Benadryl and stuff. It dries me out. Makes me thirsty. So I just cough instead. All right. So, first you got to draw the line that separates metals and nonmetals, and it's a stair step. I'll cough while I do this. Y'all are going, ooh, I'm glad she's not too close to me. I think I've already had COVID. I got hired here in the spring, and I was supposed to start March 16th, the day y'all all went home. I was going to be the new forensics teacher. But right 2 weeks before that, I was really sick. And I lost my sense of smell. I was smelling this towel, going, I can't smell. I can't smell. What's wrong with me? Why can't I smell? And this was before they came out and said that was a big sign of COVID is you couldn't smell. And I went to the doc in a box, you know, the urgent care at New Hope, and she looked at me and she said, I don't know what's wrong with you. It's like you have pneumonia, but your lungs are clear. You got something weird. And you never want the doctor to say, you've got something weird. You want them to say, I know exactly what you have, and this is it, and it's easy to fix, right? So, but I'm pretty sure that was it, because COVID was new. The doctor didn't know what it was. They didn't test me, but I lost my sense of smell, and I had every other symptom, every other one they list. It's like, oh, yeah. So I think I've already had it, and I think I'm immune, but I don't know. All right, so anyway, there's the stair step. And what I want you to do is we're going to color, we'll use blue over here, right here, one color, a line, and then I want you to make another color, we'll do pink, that'll be pretty. And then I want you to label these, we'll use red again. These over here on this side of the stair step are metals, and on this side of the stair step are non-metals. So those are our two main areas of the periodic table. We're not going to color on here yet. We're going to color those different. So from the stair step over this way, they're metals. From the stair step over that way, they're non-metals. Any questions about that? Okay, the next thing we're going to color, got to go over here to do it, is, so we've done metals and non-metals. Now we're going to do metalloids. And how I want you to color metalloids is with little lines. Because metalloids have other designation besides metalloids. And I want you to draw lines through the ones that touch the stair steps. This is the metalloids. Now, different periodic tables will disagree about what's a metalloid and what's not. I think the easiest way to remember it is what touches the stair step. So draw lines through those. But yeah, you'll see, like I think the Army periodic table that's in your drawer doesn't include all of these, but other periodic tables do, so we're going to include all of those. Okay, next we're going to go back. Oops, go down again. This thing is so much of a pain. We're going to do the noble gases. What color should we color the noble gases? Let's color them yellow. Okay? So draw a little yellow next to noble gases. And now we're going to color the noble gases yellow. Where's one of my resident experts? Who had a noble guess and can tell me where they are? Didn't someone have a report they put balloons on? Who had argon? Anybody have argon in here? No.
Someone had it.
Who had it? Because y'all remember it? This is the noble gases. Color them yellow. Or whatever color you want. I don't care what color you use. You can just, you use whatever color you need, but those are the noble gases. Now, let me tell you something about your reports. Notice how some of the reports are up on the wall. Do you see those? And back there? If I took your report and kept it, because I thought it was so great, I gave you 5 extra points for me stealing it. If you really, really, really want it back, I'll give it back to you, but I'm taking the 5 points away. Okay? So some of you, I stole your report, and they are not in for the pile for you to take them. I'm getting the pile out. I want you to take your reports today when you leave. But if yours isn't in that pile, that means I stole yours. It was so good, I had to have it. And I wanted to show it to next year for them to see what a really good report looks like, or I wanted to decorate my room with it. Yes?
In the corner, OG, it's in 2.
It's what?
Is this supposed to be both of them?
Yes, and that's why I told you to do lines here, because these will be different color. Some things will be 2 things.
Also, staring.
Because
It's hard to see, like, that half of the periodic table. I can't
Okay,
really see it.
well, I'm going to go up and get the color for the next one, and then we're going to do that. Okay, so our next one is the halogens. So, who had a halogen for theirs? Who do anybody have chlorine, fluorine, bromine, iodine? Anybody have those? Where are the halogens on the periodic table? They're over here next to the noble gases. So color these. I'm doing them green because chlorine is a green poisonous gas. It really seems like a gas Joker would use. And so it should be green. Okay, so those are our halogens. So mine's going to be green. Next, we're going to do the alkali metals. I think I'll do them orange. So you do them whatever color you want. I'm going to make them orange. Where are the alkali metals? Who had an alkali metal for their report? Anybody know where those are? Y'all were saying them when you did your report. I was hearing y'all say these. Which one did you have? You had potassium. She's right. There they are. Oops, I made a mistake. There are those. I'm going to need to erase that right there. Let's erase that while I'm at it. Oh, mine's looking prettier now. It's this first column. They're very reactive. And I found out from Miss Weeks that I'm not allowed to play with these here. They have a ban on them here. At my old school in Cobb County, I would order sodium and throw it in water, and it would burn and fizz. One time I caught the school on fire doing it, though, so maybe they're pretty smart to ban me from being allowed to play with it. But what happened was I had done this dozens and dozens of times. You get a little piece of sodium, you throw it in the beaker, it fizzes, it smokes, and on a good day it goes poof and it catches on fire, which is really cool. Floating, fizzing, on fire metal. But one time I did it, and I put it in the big beaker of water, and it went kaboom and caught the ceiling on fire. But whoever designed the chemistry room was wise enough to make the ceiling flat tiles flame retardant, and it burned itself out after about that big of a hole in the ceiling. I don't know why it did it. I had done this dozens and dozens of times, and it was just fine. I think it was contaminated. I think it had like some potassium or something further down. It gets more reactive the further down you go. Sodium shouldn't have done that. There's no reason sodium should have exploded and caught the school on fire. But anyway, we won't get to do that. Ms. Weeks said, Paulding County says no. All right, so now how about our next one? Where are the alkali earth metals? Let's make them pink. Where are alkali earth metals? Anybody have those? They're right next to them. They're right there. Alkali earth metals. Let me color code my thing. Alkali earth metals are going to be pink. Okay, our next one are the transition metals. I'm going to make them. What's a good color for them? We'll make them red. They are this square right here. Oops, I kind of went too far. And actually, I need to take a little of this off. Let's see if that will let me take off what I need to. Eraser, will you let me erase? I need to erase that. Nope, it won't. Try it again. And I'll color more carefully this time. It should not include that. All right, those are the transition metals. So I made mine red. The next one we'll make it gray. The actinides are these right here, this bottom row, and the lanthanides I'll make pink, are this row right here. So lanthanides are actually that, and actinides would be that color right there. Can I roll it up? So actinides are gray, or mine are gray down here. Lanthanides are those pink ones right there. Now our next one is we need to add, and I left it off. Oh, I put that in the wrong color. That was supposed to be pink. Lanthanides are going to be pink. Okay, add this to it. Go back to your non-metal color and color these, that color, because those are non-metals. And then I want you to add other metals. Mine are going to be orange, but, oops, wrong color. Wrong thing. I need to make it orange here. I want you to color these, that. Remember how I told you, I guess you're really a metal, but you're a halogen too. Color it like that. Those are other metals, and you know these are metals. Lead, you know that's a metal. Tin, you know that's a metal. That makes sense? All right, so that's these notes. Our test is going to be Thursday, and I'll see you soon. Science is great.